Hello everyone. So we can continue with the lectures now, and we can get into the core optimization methods. So the plan is first we will start with some of the basic maths, you can say, or the geometry, you can say, that is needed to do optimization methods. So we will continue with that, and then we will discuss the solvers, the different types of solvers based on the gradient methods and so on, variety of models and so on. So let us continue with what I call gradient and geometry. So let me check. Okay, so so the first question that we have in mind is why gradients, why we are interested in gradients. Well, from calculus, what we can recall is that gradient points in the direction of the increase of the function. Okay, so if we take gradient of a function at a point, then it points in the direction of the increase. Okay, so the vector direction tells you that if you go in that direction, it will increase. Hence, negative of the gradient, which is here, so negative of the gradient will give us the direction of the descent. Okay, so we have a direction of the ascent, which is the gradient. So gradient of f of x gives us the direction of the ascent. Okay, if you follow that direction, if you follow minus negative of the gradient of f of x, then you descend. Okay, descent means going down, ascent means going up towards the direction where the function is supposed to increase. Okay, and given a function, in this case it's like a two variable function, so let us say we can write like this, fxy. Okay, so the values that you get, z is the points on the surface here. Okay, and xy is are these variables. So in the earlier classes, we have said that if we want to get a critical point, then we equate the gradient to 0, right? So this is what we mean by that. So all the set of critical points where the function will have a maxima or minima, right? So this is the local maxima here, this is the local maxima here, and then there is one minima there. Okay, so all the set of points where your function can have maxima minima is given by solving this gradient of f of x is equal to 0. So you collect all those x. Okay, so one x that you got is here, another x that you will get, x star that you will get will be here, another x star will be here, another one will be there at the bottom. So these are the places where the function can take either maxima or minima, and then you need to do the second derivative test to check whether the point is whether a minima or whether it is a maxima. Okay, so these are the basic ideas. What you see here is a so-called level curves. Level curves are a tool to work in a 2D. Okay, although the function can be 3D, but using the level curves, we can try to understand how the function is behaving. Okay, so if you look into the level curves here, so these are the level curves of this function fxy. Okay, so if you get a level curves like this, then you know that somewhere at the center there is a maxima or a minima. Okay, how to plot level curves I will discuss in detail. Okay, so what are the things we want to know today is what is a level curve and where does gradient points to. But well, gradient points in the direction of the increase, that's like a fact that we have from the calculus. And how does gradient help in going to the minima? Okay, so first question is what is a level curve? So level curve of a scalar valued function. By scalar valued we mean that the output is a scalar. Okay, So these are called scalar valued function. This is a multivariable but scalar valued. Okay, multivariable because the input is a n-dimensional vector. Okay, so there are like n variables. So it's a multivariable real valued function. Okay, so multivariable real valued because the value it takes is real. Okay, it's a real valued function. And the level curve, our focus is to understand what is level curve of a real valued function. So this is defined as follows. So f of t is the parameter here. F of t is the set of all x, y such that, okay, I mean, this is an example of R2, you can say. I've given this for R2. So that's why I have two components in the vector x and y, two variables. Okay, so the function that we are considering is R2 to R. Okay, so this is multivariable and real valued. So for this case, let us say the level curve will be defined like this. So what is the level curve? Set of all x and y such that fxy equals to t. Okay, and you are allowed to vary t. Okay, so t is something you will vary. Okay, so for instance, I can ask what is f1. Okay, so the set of all. So then we have to calculate the set of all x, y such that f of x comma y is equal to 1. Okay, so you have the plot of a function, right? And so some surface plot is there. Then you have to find all those x, y in your domain such that your function height is 1. Okay, so it could be like various places where the function height is 1. So these are called the level curves of a function. If you go back here, if you see, then if you take a slice of this, so let us say I fix t to be this guy. So let us say t is this. Okay, then I'm taking a slice of this curve, horizontal slice of this curve at t, and then I'm saying what are those x and y for which I'm getting this slice. So these are the things, right? So in this case, it will be some circle. Okay, some circle like this. Okay, so this is f of t. Okay, so f of t is the slice of the function. Okay, and the height of the slice, vertical height of the slice is t. Okay, so this is how the level curves are defined. Okay, so so here is the quiz for you. Draw level curves of the following function. Okay, so we need to draw the level curves of the following function. So let us say if we would like to discuss the level curve of this, which is fxy is x square plus y square. So what could be the level curve of this, right? So let us see. So as we said, so the t is given to us. So t is 0, 1 or 2. Okay. So let us say for t equals to 0. Okay. So for t is equal to 0, let us compute the level curve. So t equals 0, it will be f of f0. So this is set of all x, y such that f x, y is equal to 0. Okay. So these are the set of level curves. So this means that what I'm asking for is set of all solutions to this equation x square plus y square is equal to 0. This is what this means, right? So x square plus y square equal to 0 has only one solution, which is xy is equal to 0, 0. Okay, that's the only place where this equation is satisfied. Now we can ask for f1. So f1 level curve will be set of all xy such that fxy is 1, right? So this means x square plus y square is 1. Well, we know that set of all xy that satisfies this is a circle. Okay, circle with right. So circle with radius 1, right? So 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 this is the circle, right? But in this case, it was just just the origin part, right? But here in this case, it's a circle. Okay, so it's a circle. It goes with a radius of 1. So this is the another level curve, and then you can also ask F2. Well, F2 is again nothing but x square plus y square is 2. Okay, so so in this case it's like a circle with radius square root 2. Okay, so square root 2, so circle will be somewhere somewhere here and so on. So this is how you get the level curves. Okay, for this function. Similarly, you can try level curves for this function. Okay, so this is how you plot the level curves. And why are we interested in level curves? Because it gives a 2D view of a 3D function. Okay, so this is a 3D function. Okay, so x square plus y square will be above the plane of the xy plane, right? But to visualize this, I cannot visualize 3D, right? So then I can look into the level curves, and this tells me this gives me some idea of how the function might be behaving. Okay, where it may be increasing, where it may be decreasing, and so on. So these are the examples of level curves. Okay, so this is some function. This is again some two variable function fxy, and that looks like a surface. And these are the level curves that you are seeing here. Okay, so these are the level curves that you are seeing here. So when you have these concentric circles like this, you immediately identify that there is some maxima or minima happening here. Okay, you cannot really precisely say whether it's maxima or minima. Okay, but yeah, but because even in this, unless you know the heat map also. Okay, because even for the maxima, let us say this guy, if I start putting the slices, then the slices will here it will look like this, which will look very similar to the slices that you get in the maxima also. Okay, so but the key point here is that it can tell you whether you can go to the local minima or local maxima or so on. So on paper, we may want to have some geometrical feeling of how we are proceeding towards maxima or minima by drawing the level curve. So I may start from some point, and then my goal is to go to, let us say, minima here. So I will go in some directions and some direction and something like this, and then I have to eventually reach there. Okay, so level curve is a tool to study 3D functions, you can say. If it is even high dimensional problem, we have no hope. Okay, so okay, so level curves can be very strange. So this is the graph that it is trying to say. You can see that the function has a lot of ripples, and hence the level curves also look very very chaotic and so on. Okay, so and these are actually the cases that you see in the artificial neural networks that we will study shortly, where the objective function or the loss function that you are trying to minimize, your parameter of your model. So the loss function, if you plot the loss function, well, neural networks are very high dimensional loss functions, but even if you plot a slice of that, they look very chaotic. Okay, so very like up and down and so on. So the main problem of optimization is to locate a minimum loss for your function for the given set of parameters. So these are the parameters of your model, right? So this x and y could be the parameter of your model, and loss can be, let us say we parameterize this by x and y. So we have the loss function defined, and then we have to look for some x and y for which my model loss is the minimum, right? So let us say if that point is here, okay, but this is something you don't know in advance. That's the problem, right? Even plotting is not easy for very high dimensional problem. In this case, it is still only 2-dimensional problem, so you can plot and see, but we are talking about very high dimensional problems. It can go up to, let us say 1,000 is a very modest, I would say. So you can go into very high dimensional problem like even million and so on. So even simple things like plotting, or because you cannot eyeball and say that okay, there it's the minima, right? So these problems are very high dimensional and so on. So that's the whole point of optimization method, to come up with algorithms that can at least step by step proceed towards the minima of this. So so you will start randomly because you have no idea where to start with. So you will start somewhere randomly and you will start searching in a step by step manner. Okay. And then somehow you expect that your algorithm will reach to the minima. Okay. Sometimes you are unlucky, then you will start and then you will get stuck into some local minima. Okay. But usually, like, even this local minima may be doing good enough for you. Like even if you do, maybe it is generalizing. Okay. Okay. So yeah, we will get into these things, but in general, given a function like this, then the whole idea of the optimization method is to find a set of algorithms that can work on very uh, very rough graph like this. So I mean, you can intuitively say that it's already a very hard problem, right? So we have to really study this systematically, and that's the goal. So level curves are a convenient way to show directions towards minima or maxima. And as I said, the gradients point in the direction of the increase, right? So that's the whole idea behind the gradient based method, is that gradients point in the direction of the increase. Okay. So for example, here is the minima, right? So if you are here somewhere, okay, if you are here somewhere and the function is increasing, if you go in this direction actually, like rather this direction here, then the function is increasing. Okay, so function is increasing and gradient points in the direction of the increase actually. So if you take a gradient here, then it is telling you that actually you are going in the direction of the increase, and but your objective is to find the minima, so you will take the negative of the gradient, and hence from here you get some idea that maybe I should go this way. Okay, but obviously you may get lost in a variety of ways, right? Because things may be like this, right? So so rather than going to the global minima, so yeah, so you will get stuck here only, right? Because after this you don't know, your gradient vanishes here. Okay, so your gradient vanishes here, so after this you don't know what to do, because here you are computing the gradient of f and it's coming out to be 0. So you don't know after this what to do, right? So on a very yeah, so gradient does tell us, unless it vanishes, gradient does tell us the whether the function is increasing or decreasing in a certain direction or not. Okay, so this is something we will discuss in detail again. But what is most important when we want to use level curve as a tool to study optimization methods, then one of the things that we need to establish is something something like this. So in which direction gradient points to. Okay, so the fact is, like, if you draw these level curves and if you are at point x, let us say, and if you draw the tangent to that point, tangent to the curve, level curve at that point x, then the gradient always points perpendicular. The gradient is always perpendicular to the tangent on the level curve. Okay, so remember, we are building tools to analyze a function using level curves. So one of the things that we want to understand is how gradients are related to the level curves. Okay, so what we know now is, like, tangents are perpendicular to the level curve, and this is something like we can prove. Let us say let us go ahead and prove this. Okay, but to prove this, we will need something called implicit function theorem, which is as such, it's a simple fact. Okay, so and this comes from this multivariable calculus book by Apostol. So what it says is easy. So let us read this. So the reader knows that the equation of a curve in the xy plane can be expressed either as in an explicit form, such as y is equal to f of x, or in an implicit form, such as fxy is equal to 0. Right. So to give you an example, let us say y equals to 3x plus 4. So this is an explicit representation of the function, right? So y, I explicitly write y as 3x plus 4. Okay, so that's an explicit representation of the function. But another possibility is to write it as y minus 3x minus 4 is equal to 0. So then I write this as fxy is equal to 0. Okay, so this is the implicit form and this is the explicit form. Okay, but the important thing is like explicit form can happen only in some cases. I mean, it's not possible to write in explicit form all the time. Okay, so let us see how. So however, if we are given an equation of the form fxy equal to 0, this does not necessarily represent a function. Okay, this doesn't represent it. So moment someone gives you fxy equal to 0, there is no guarantee that you can explicitly solve for y, or the more precise way to say is that it will form a function, right? By function we mean that you don't for a given input you have only one output, right? So that those are the valid relations. If you recall the definition of a relation, then for a single input you must have a I mean, yeah, I mean relation is fine, right? So but what you don't have is the function here, because function, there is a requirement is that for a single input I could not I cannot have multiple outputs. So for instance, here is my some variable x, some value x, let us say, then the function should have only one output. Okay, for a function to be well defined, for a given input my function cannot have two different outputs, so it cannot have double outputs. Okay, that's not a valid function. Okay, for a given input I must have a unique output. I mean, you may say like, what about functions that that are like this? So let us say it takes xy and it produces outputs like this: x plus y, x minus y, right? So you may ask questions like this, that what about these functions where I have the input and I have like outputs like this, but this is not a multiple output. This is a single input, single input, single output case, because the function, the way function is defined is R2 to R2. Okay, so for a single input vector you have a single output vector. Okay, so that's okay, that is still a valid function. Okay, so what it is trying to say here is the equation fxy equal to 0 does always represent a relation, namely that the set of all pairs xy which satisfies the equation. Okay, so as a relation it is fine, but as a function it may not be. It may not be a valid function. So you can take an example like this: x square plus y square minus 5 equal to 0. So this is nothing but a circle. Okay, so this is a circle, x square plus y square is equal to 5. Now this doesn't represent a function, because for any input x here, okay, let us say x here, I am getting multiple outputs here, right? So this is output here, and there is another output here. Okay, so function for a single input I cannot get double output. Okay, so this is not a function. So but so let us read this. So the following question therefore presents itself quite naturally. When is the relation defined by fxy equals to 0 also a function? Okay, like for instance, if I consider this, then this is a function. Okay, so this does define a function, which is in this case it's a line. Okay, so pair of xy, you can so plot this, then this is a line. But in this case, if you plot those pair of xy, then this is not giving you a function. Okay, at most it's a relation but not a function. So some fxy can be treated as a function like this. In this case it's a line, but some fxy equals 0 may not form a valid function. Okay, So so the following question therefore presents itself quite naturally. When is the relation defined by fxy equals 0 also a function? In other words, when can the equation this be solved explicitly for y? So can you solve this explicitly for y in terms of x and yielding a unique solution? So for instance, we had this counter example here. So x square plus y square is 5, and try to solve this for y, right? So this y square is 5 minus x square, and y would be plus minus square root of 5 minus x square. And what this is asking here is a unique solution for x, but you don't get unique solution for x. If I put x equals to 1, then I get plus minus of 2. Okay, so y equal to 1, I get plus minus of 2. So I'm not getting a unique unique output. Okay, for a function I must have a unique output. So if you break this circle into two half like this, then the upper half indeed becomes a function, because for a unique x there is unique y. Similarly, the lower half becomes a function. But together, because of this plus minus, so the upper hemisphere and the lower hemisphere, right? So together, if you put them, then it's not a function anymore, right? So this is what this function is trying to. So this is the theorem here. So implicit function theorem deals with this question locally. So implicit function theorem tells you that okay, I agree that I cannot treat fxy as a function as a whole, but what about locally? Like, is it possible that locally I can treat this? I can treat this um, as a function. So that is true actually. So locally, if I look into this portion of the function, then locally it is fine. For unique x, I have unique y. Locally, if I look into this, then it's fine. For unique x, I have unique y. So locally, I can explicitly solve for y, but not as a whole. Okay, so intuition behind implicit function is rather clear, that locally you can do. So okay, so the implicit function theorem deals with this question locally. It tells us that at point x naught y naught, such that the x naught y naught is in satisfies that under certain conditions there will be a neighborhood of x naught y1 y naught, such that in this neighborhood the relation defined by fxy equals to 0 is also a function. Okay, so what it is trying to say is like some neighborhood, let us say x naught y naught. So let us say some x naught y naught is here. Okay, okay, so this keeps overwriting. So let us say I have a circle, and then I take some neighborhood here. Okay, so along this neighborhood I can explicitly solve for y. Okay, so that is what is implicit function theorem. So given any arbitrary curve like this, for instance, if someone asks you, is this a function? Definitely it's not a function, because for a unique x, I'm not getting unique y, I'm getting multiple of the y's here. Okay. Similarly, if you ask here, so then I'm getting multiple of the y. Okay. So for the same x, I'm getting 2y, right? So this point could be like x1 y, and this point is like x2 x1 y y2 actually. So yeah, so x1 y1 and x1 y2. Okay, so for the same x you cannot have two for the same x you cannot have two different y. Okay, so x1 y1, and then you have x2 y2, but this is not allowed. These two things are not allowed in a function definition. Okay, again I'm making mistake here. Yeah, there should be one here. Okay, okay, yeah, so you get it. So here so this is another curve, and it is not a function as a whole, but what implicit function tries to tell you is like locally you may be able to apply the implicit function theorem. Okay, so there should be a small enough neighborhood where you may be able to solve for x and y. Okay, so that's what implicit function theorem is trying to say. So locally, if I look here, then if I consider this area, then I can explicitly solve for x and y, because there is no conditions like this. For a same x, I have two different y. Okay. Similarly here, locally here I can do, because if I have consider this local domain here, then definitely these guys are included. Okay. So now there is no ambiguity here. So for same x, I have two different y. So this is the basic idea about implicit function theorem. But what is the takeaway from here is that given fxy equal to 0, locally I should be able to solve for either x or y such that it is a function. Okay, so it could be either solve for x or it could be either solve for y. It doesn't matter, but I should be able to solve, provided I am in a small enough domain. Okay, a small enough domain. By that I mean, like, your curve can be like very, let us say like this, right? So here, if you want to make the local thing, then you have to have a small thing here, right? So a small circle here, and here also we have to have a very small circle here. Okay, the intuition is like this curve should not self-intersect. That's the important thing. As long as they don't self-intersect, okay, I can always form a neighborhood where there is no ambiguity, because there is a space, because they are not self-intersecting. So there will always be a space such that I can draw a small enough neighborhood, and then I can explicitly solve for that in that neighborhood. So that's the implicit function theorem. So even curves like this, if you can see, since they don't self-intersect, I can always form small neighborhoods, right? So let us say I form a small neighborhood here. So along in this small neighborhood, I can explicitly solve for x and y. Excuse me.
Sir,
So this is Hilbert's curve.
sir, I had a question.
And yeah, so implicit function theorem can be applied. Now let us go ahead to prove the fact that the gradient of a function is perpendicular to the tangent on the level curve. Okay, that is what we started with, right? So that was our original plan. So let us see, we can write our function fxy, and let us say fxy is equal to w, and a level curve looks like this. So fxy is equal to some constant c. Okay, so that's how the level curve look like. So by implicit function theorem, we can write like this: y is equal to some function of x. Okay, so y can be written as some function of x. So this is how it's like, we denote it, like y is a function of x. Okay, by implicit function theorem, like, let us say we may not be able to do it globally, but at least locally we can do. Remember that level curves are like a closed loops, right? Especially near the maxima or minima. So level curves look like this. Okay, so definitely they are not really a function, but locally, let us say I focus here locally. So locally I should be able to solve for y. Okay. Okay, so the level curves will look like this. So in place of y, I write this as y of x. Okay, so whatever the expression of x that I got after solving, I put that expression of x here is equal to c. Now we can apply the chain rule. So if we apply the chain rule, then what do we have? Okay, so if we want to do del f by del x, okay, so if we apply the chain, so we have del f by del x, and then del f by del y, and del y by del x. Okay, so this is a function of the form right like this. Okay, so if we recall calculus, if I want to take a derivative of df with respect to dx, then what I have to do is I have to do del f by del u and du by dx plus del f by del v times dv by dx, right? So this is what we know. Okay, so let us say if you forget, then this is what we have. So in this case, like u is like x, and v is like y. Okay, so if I write this in this form, So in this case, df by dx is df by dx, so okay, or del f by del x times, and in our case u is just x, so it's like dx by dx, so that's just 1, okay, plus and del f by del v, okay, so in our case v is y, so del f by del y, and then del v, so our case is v is y, so so dy by dx, okay, and dy by dx of a constant in 0, okay, so that is 0. So from here we can solve, from this equation we can solve for dy by dx, which is minus del f by del x divided by divided by del f by del y, okay. So so the tangent vector to this level curve um, uh, will be this, okay. So this is like the slope of the tangent to the level curve, okay. So the tangent vector itself will be a vector like this, right? So see if so this is the level curve I have, okay, and then there is some point here, some point here, some point here, x and y, and then the tangent here is nothing but dy by dx, right? So this is the tangent, and the slope of this is given by dy by dx, okay, and this is the slope that we found here, okay. And if you want to write this as a vector, right, so if someone tells me slope of a line, right, so if someone tells me slope of a line, then I can make a vector out of that, right? So this will, so in terms of vector it will look like this. So you just take the numerator and then you take the denominator, right? So let us say someone tells me slope of a line is let us say someone tells me that slope of a line is let us say 3, okay, slope of a line is 3. So then can you tell me a vector on this line? So can you tell me a vector that is along this line? Okay, that's the question we are asking, right? So what is the vector now? What we have found is like slope of the tangent, but then I'm asking like what is the vector along this line, right? So one possible vector along this line, because this is the slope, right? So slope of a line is given to me. So the slope of some line is given to me, and that someone told me it's 3. So from the slope I can like make out what could be the vector in this direction, okay. Remember vector could be this, here, it doesn't matter, but what I'm asking for is it has the same slope, right? So I can make it as 3, 1, okay. So if I take 3, 1 vector, okay, so if I take a 3, 1 vector, let us say 3, 1 vector would be somewhere here, okay. So 3, 1 vector has the same slope as this, so that's how I get the tangent vector, right? So that's what I did here, okay. So I had the slope, so I took the denominator, I put it here, and I took the numerator and put it here, okay. So someone gives me slope, then I can get a vector out of that. So that's what I did here. Okay, now what we want is a gradient, okay. So remember what was our original goal, right? So I have a level curve and then I have a tangent vector, and what we want to prove is the gradient of f is perpendicular to the tangent. So what we have found is a tangent vector, okay. So tangent vector we have found will look like this, and now we are looking for gradient, expression of the gradient of f, and then we will see whether they are perpendicular or not. So gradient is given by del f by del x, del f by del y, that is known. So the slope of this is this, right? So now it's a question of the vectors being perpendicular or not. That is what we started with. So gradient of f, and if you do a dot product with the tangent vector, it will come out to be 0, okay, and that would mean that the vectors are perpendicular, right? So a vector u is perpendicular to v if u transpose v is equal to 0, okay. That's how we know from linear algebra. two vectors are perpendicular, okay, when their dot product is 0. Okay, so but this is what is happening here. So if I do T transpose of grad of f, okay, if I do that, then they become 0, right? Because it becomes del f by del y, del f by del x plus del f by del x times del f by del y. But this is a negative of this, so they get cancelled and I get 0. So this is a concrete proof of the fact that a tangent drawn on the level curve, so I mean the gradient of a function is perpendicular to the tangent drawn on the level curve. Okay, so this will help us in the analysis during the analysis part of the optimization solvers. So then it will help us track where we should go in reference to the level curve. Okay, so this is the direction of the ascent, gradient is the direction of descent, and I have to go perpendicularly inside, right? So I will draw a level curve and then I will draw a tangent, and to minimize I have to go inside. There will be another curve, level curve, after some point, and then I will look at the tangent, and then I will draw a perpendicular, and then I will know the direction of the gradient, and then I will go inside. Okay, so this is very annoying in this annotator that it just selects and it doesn't allow me to write again. But anyhow, you get the point. So you can keep, so you know now how to move in accordance with the level curve. So each time you will draw a tangent at the current point, and then you have to go perpendicular to the tangent. So if you want to increase, then you have to go inside. You will go in, you have to decrease, then you have to go inside, and increase, you have to go outside. So these are the tools that let us analyze the problem and how we can move. Okay, so the proof can be extended also to 3D functions. So I'm going to skip this this proof, but I can hand out the I can give you the, so what the proof that I did was for 2D, but proof again is simple enough. Also we can generalize this. So yeah, the natural question that that comes in our mind is why are we interested in gradient? So by now you get the intuition of what I'm trying to say, right? Gradient points in the direction of the increase. We have to follow the negative gradient direction. If we want to minimize our function, then we have to follow the negative. If we want to maximize our function, then we have to go to the positive gradient direction. So gradient gives you a very nice tool to at least start looking for the maximum minima, because it is telling you locally, at least it is telling you where the function is potentially going to increase and where the function is potentially going to decrease. Okay, so that's why gradients become important in optimization methods. So why gradients? Well, a negative of the gradient gives me the direction of the descent, and usually my goal is to solve optimization problems like this, minimize fx, and I will start with some random point, and then I will follow the negative gradient direction, and then I reach some new point, and then I follow negative gradient direction from this point, and this way I keep doing, and then at some point I should arrive at least at a local minima. Okay, that's what gradient method can ensure, that you will arrive at least at a local minima. Okay, so this is why we are interested in gradient. Okay, and this is the same picture that I said before, but now we can draw level curves, and then we can, each time we draw perpendicular, we go inside, each time we draw perpendicular, and then we go inside, and this process continues iteratively. So we have answered two questions. What is a level curve? So I gave you a definition of the level curve. How do you draw level curves? So there will be an assignment where you have to draw level curves of some functions. And then second question was, where does the gradient point to? So gradient points in the direction of the increase. That's a fact from calculus. So I have not given any concrete proof for that, but that is something we take from calculus. And how does the gradient help in going to the minima? Okay, so that's something I've given you a good amount of intuition by now, why it should help. Okay, so let us write our first algorithm to solve the minimization problem iteratively. Okay, so as I said before, the minimization thing that we did before in the previous lectures, where we solved some problems like in the area rectangle, and then we solved some problems with that involve like first variable cases, and we could explicitly solve those equations and so on. The reason why we have to go with the iterative method is that the functions are of very high dimensions and we cannot solve problems explicitly. In fact, even finding the critical points is not an easy task. So if fxy is complicated, then even to know the points are critical points is not easy. Okay, imagine that the function is very high dimensional and highly nonlinear. Let us say it's like this. Okay. Uh, um, something like this. I've cooked up something like this, and it may not be easy for you to actually find solutions. And this was just a single variable nonlinear case. But if I make this into a very high dimensional like let us say multivariable problem, so it has like many variables x1, x2, x3, and so on. Okay, so then the function could be very chaotic, right? So x1 square plus x2 square sine of x3 e to the x3 plus cos of x1 square plus x3 square. Okay, so if there is a function like this and you have to minimize this over the vector x1, x2, x3, then your first step could be is like, okay, let us go ahead and find the critical point. But even finding this may not be easy. Okay, and this is still only 3 variable case. Imagine that you have like 1,000 variable case and so on. So even solving for the critical point is not a straightforward thing. Okay, so that's why we go for some iterative approach. So iterative approach, the idea behind iterative approach is that given a function like this, you start from some random point and then you go step by step. Okay, following some tool, like gradient method is one tool. Okay, so that is why the direct approaches doesn't work anymore. Okay, so we have to go with the iterative approach. Okay, so we have told this many times now that gradient is an important tool for us, and that will allow us to go step by step to the minima. Okay, so this is the first algorithm, gradient descent algorithm. So name descent here means that it's in the context of minimizing the function. Okay, so you want to descend. Okay, it's like a hill, and to find the minimum of the hill, you have to go and you have to do the descent, go down, right? So the basic algorithm tells the following: start from the initial guess x naught, x0, and from the current position, move in the direction of negative of the gradient. Okay, so from vector calculus point of view, what does this mean, right? So you are at x naught. Okay, so let us say this is your vector x naught, and then you are told to go in the direction of negative of the gradient. So let us say negative of the gradient points in this direction. Okay, so negative of the gradient of x naught. Okay, so here you computed gradient of f of x naught because you are right now at x naught, and the negative of the gradient tells you the direction for minima. Okay, so let us say this is the direction it's pointing to, so you go in that direction. Okay, and how far you go, that is another question again. So the new point that you will reach, so someone tells you are at position u, and then someone tells you go in the direction of v, then that means plus v. Okay, that's what vector calculus tells you, right? If someone tells you current position is u and go in the direction of v, okay, if you want to know how far, then you can put alpha also. Okay, it may be a unit vector. Okay, so I'm at u and someone gave me a direction, unit direction. This is the direction v. So the place where I arrive is u plus v, right? So that is how I will move. So at current point x naught, the direction I want to go is negative of fx naught, and the place that I will reach will be x naught minus negative grad fx naught. Okay, so that's the idea. That's the idea, and then from here again you will compute the gradient. So this is the point. Let us say x1 now, the new point. Now at x1 you will compute the gradient, and then you will go in the gradient direction. So the next update will be x1, and then you're going in the negative direction. So negative of f gradient computed at x1. Okay, so then you reach some new point x2. Okay, so let us say you reach new point x2. So this way you will keep following the gradient direction and you will reach at some place. As I said, if someone tells you a direction, then another question is like how far in that direction. Okay, so there will be some scalar t here involved. Okay, so how far I want to go. So you will scale the direction, and then that will tell you like how far you are supposed to go. So you will usually put also t. So it's not just about going in a direction, but it's also about how far you should go in that direction, because you may end up into some issues like this. For example, you have a function like this, and I clearly know that minima is here. Okay, and let us say you started with some random point which is here. Okay, so let us say this is the random point x naught, and you computed the gradient. So the positive gradient points in this direction. Okay, so that's the direction of the increase. So the negative gradient in this direction. That means you are going in this direction. But if you go too far in this direction, okay, so this is the direction that you know. Okay, so you know the x naught direction, and you want to go too far in this direction. So if you choose t which is too much, then you will end up somewhere here. Okay, so this will be x naught plus t, and let us say grad of f that you computed at x naught. So in case if you take too big a t, then you will overshoot the minima that you were planning to reach. So minima you were planning to reach was here, but since you took too big t, you ended up here, which is now no longer a minima. I mean, it is like, yeah, either here or somewhere here, but your goal was to reach to minima, but you exceeded. Okay, and you hit some other place which is maybe not something you wanted. Okay, so how far you go, so this is called the step length. Okay, so how far you go in a certain direction is also important. Okay, and you have to run an iteration, and you have to run it until you are satisfied. Okay, now a question is like when are you satisfied, right? So one thing I know is like one possibility when I will get satisfied is like when I reach the minima, and the point where I reach the minima, gradient of f will vanish. Okay, so that's when the tangent becomes flat. So gradient of x must be vanished. So one way to know is when to stop this algorithm is that you compute the gradient of f, and you can take a norm of the gradient of f, and if it is 0, then you know that tangent has become flat. So possibly I have reached a minima. Okay, numerically you may not get an exact 0, so sometimes you may have to stop at -9 or -10 depending on whatever. So it's like not exactly 0, but it's like almost flat. Okay, because numerically sometimes 0 may not be easy to achieve. Okay, the real issue you may face is when it is a very shallow minima. So by shallow minima I mean something like this. Okay, so it's like tangent is becoming flat, 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 but how long you will run it, you don't know, especially if your step length is very small. So let us say step length is are like, you are very cautious, right, that you don't want to overshoot. So you will get bored, right? So you are going and your tangent is like becoming flat. So it's like if you take the norm, then it's like already -8. Okay, then you are getting to -9, but it's going very slowly. Okay, so -9 and -10 and so on. So there are some judgments that you have to make, that because minima is there, but it's like very far. It's like almost getting flat and so on. So you may stop at some point and say, okay, I'm happy with this minima. Maybe this will generalize the model as well. Okay. So these are the decisions that's up to a user actually, because some functions may have very like wide basin near the minima or the maxima. So, but the only issue is like we may not be able to predict these things. Okay, so unless we really run it for a long time. Okay, so when do you stop? Usually people will stop with some some tolerance like this, 10 to the minus 10 or whatever they, sometimes even a 10 to the minus 3 or whatever. Okay, so it depends on the problem at hand. So stopping criteria it depends, but the most important thing is that your algorithm is going in a correct direction is when norm of the grad of f is actually going towards 0. Okay, so it should go towards 0. Okay, as your x is getting updated. In case it is not going to 0 and your goal, in case it's not going to 0 and it is oscillating a lot, then there are issues then you may think of, right? So if it is oscillating a lot, then one reason could be is like your step length maybe is a little bit too big. Okay, so it may be that the function is like function itself is like oscillatory behavior, and you are like starting from somewhere, and your t is so big that each time you overshoot the minima. So minima was here, but then you overshoot and you reach here. Okay, and then you overshoot, let us say, and then let us say you reach somewhere here. So you went down and then you overshoot and then you went up. So this way, if your function itself was oscillatory and depending on the choice of the t step length, you may see that the norm, the gradient of the norm of the gradient is here. It's high here. It's decreasing. Here it's increasing. So you may get oscillatory behavior. But if you have kept your step length small enough, then you may not. You may at least ensure that you get to the local minimum. So these are the things. So when to stop? It's like, as I said, if you decide that gradient of f is very close to 0, then you may decide to stop. Okay. And as you are going close to the minima, you will see that the gradient won't update because this guy is going to 0, right? So you will see that the updates you are getting in the position now is very less because the updates are happening because of the gradient, and assuming that your step length is also like modest size, not so big. So so t is, let us say, some 0.1, and then grad of f values are is a vector. So values are already like, let us say, each components are like minus 4 or something like that. So the updates you are getting in x is also up to the order of only 10 to the minus 5. Okay, so only this many, only after 5th decimal place is actually it's updating. So your updates will start getting very slow as you get close to the minima. So one thing, yeah. So when you are running the gradient descent method, one of the things you can print when your code is executing is the norm of the grad of f of x, and see what is happening. Okay, so if it is going down very quickly, then you know that it's a very steep type of function. So your gradient is like really going very, but then at some point it may happen that when you are getting closer, you have to be a little bit cautious. So you may dynamically change the step length because the amount you were traveling in this direction, if you also travel when you are close to minima, you will again overshoot. So you will go here, and then you have to come back, and you will come back. Gradient descent will make sure that you will come back because this point again you will do a gradient. It will point in the direction of increase. Again, it will tell you that decrease is this direction. So even if you overshoot, you will come back. The only thing is like your step length is so big that that you go from here, and then you reach the minima. The step length does have a lot of role to play. So we will spend a good amount of time in variety of step length and how to stabilize gradient descent methods. So there are, and even in the stochastic setting, when you have large machine learning problems, then you cannot really even hope to compute the full gradients. Okay, full gradient. So you will compute so-called partial gradients on a partial loss, so to say. So by partial gradient, I mean computing gradient on a partial loss function. So loss function that you compute will be not over all the samples, but over the selected set of samples. Hence, it becomes, we will call it a partial gradient, or another way to say is like stochastic. The name stochastic here comes also because the samples that you include in the loss is like random and so on. Don't worry if you don't understand now, but we will discuss these things in detail when we study stochastic gradient descent. But this is not stochastic gradient descent. Right now it is a gradient descent method. Stochastic gradient method is a variant of this, where the gradient that you compute is not really the full gradient, but a partial gradient. And since it's on random samples, it's stochastic. Okay, so the basic gradient method is the core in knowing other algorithms. So I hope this is very clear. I have been very slow with this part. So the basic idea of a gradient method is that gradient points in the direction of increase. Since you have a minimization problem, we will by default always talk about minimization problem. As I said, minimization of f of x, maximization problem is nothing but a special case of minimization problems. If someone tells me maximize instead of minimize, then I can change this to a minimization problem by just doing negative of f of x. Okay. So any maximization problem, I can always transform this into minimization problem. So that's why usually we will only talk about minimize, 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 and descent, descent, descent. We will never say anything about ascent, because we know that just studying minimization is enough. Okay. So that's why you will hear a lot. But in case if you want to maximize and the problem was to maximize, then the question is what changes you will do in the algorithm to transform this into a gradient descent, gradient ascent algorithm. Okay, so these are the questions we may ask, like what are the changes I will do in the gradient descent algorithm to make it work for gradient ascent, right? So idea is clear, right? So gradient, you follow the gradient direction now instead of the negative gradient, because negative gradient is the direction of decrease, and to increase we have to go to the positive gradient. So only change that you will do is that you make it plus here. Okay, so that's the gradient ascent. I have written here also. So this is the gradient ascent algorithm, and the only change you will see is that plus is here. Okay, other things like when to stop, how to stop, it's the same issue like in the gradient descent. A gradient descent has similar things, like when to stop, it depends. Like even at the maxima, the gradient is supposed to be flat. Like this is a maximum, so gradient is going to be flat. So you will again check whether the norm, even for ascent, you will check whether the gradient norm of the gradient is becoming 0 or not. Okay, if it is becoming 0, then you can say, okay, that may be the potential maxima that I have found. Okay. Another possibility is to check is whether the updates you are getting are small enough, because if the updates you are getting are small enough, then this also means that the gradient is likely to be very small. Okay, so gradient may be very small. That is why the updates difference between xi and x and the previous xi are not really big. So these two things you may use to make a stopping criteria for this. Otherwise it's an infinite loop, but to stop we may use either this or either this as a stopping criteria. Okay, so a brief history about gradient descent method. So gradient descent method was proposed by a French mathematician, Augustin Louis Cauchy. Cauchy was involved in variety of other contributions ranging from physics, astronomy, and I believe complex numbers and so on. Okay, so so this is a brief history of how the gradient descent method came, and gradient methods are really the workhorse. As I said, there are more advanced variants of this and a lot of changes and so on, depending on the problem at hand, whether you are solving a computer vision problem, whether you are solving a robotics problem, whether you are solving a data science problem. So there will be quite a wide variation to this, but the basic underlying idea is actually the same. Okay, the basic idea is the same. We will try to give a general framework, and that is called steepest descent. And then we will see that with a nice set of tools, maths tools, we will see that it's a matter of norms, right? So the norm in which you are you're dealing with will give you, from there you can derive variety of methods, like even Newton method, okay, and so on. So coordinate descent method and so on. So we will put that into general framework, but the main idea behind all this is indeed gradient descent method. So it's worth looking into the original author and how they came up with this. Okay, so original author, the goal of the original author was to solve simultaneous set of equations, and this could be like nonlinear set of equations, simultaneous, and he's saying that explicitly you cannot compute it because it may be by doing explicit eliminations you may get into even like complicated expressions which you cannot solve. Okay, so this goes in line with what I told you before, that if someone gives me a very highly nonlinear function fxy, then even solving for the critical points is not an easy task. Okay, so that's why we are interested in the iterative methods, where we have the loop and then we update our x from time to time. So that's why he went ahead and then he considered this function like this. So this is a 3 variable function. And then I'm like speeding through this, just going through the main points. So in his original paper, which was written like maybe 100 years ago or more than 100 years ago, like 1800 or something. So in this case, he's talking about the gradients of x, y, and z. So this is like the gradient of u with respect to x, with respect to y, with respect to z. And then he's also talking about the step length alpha, beta, and gamma. Okay, so let us see the algorithm that he described. So this is the algorithm that he came up with. He said that the updates to the x, y, and z that so the way he is trying to write is like this. So let us say this is my current x, and I update this as current x, y, z, and I update this as alpha, beta, and gamma. Okay, he wrote this same thing in a component wise way, but I wrote this in a vector form here. And what he is trying to define alpha, beta, and gamma is, so we can substitute what he's trying to say. So x, y, z, and what he's trying to say is minus theta. And remember, x was the derivative of the function, so dx of u, right, and dy of u, and y was dy of u, and z was dz of u. Okay, so alpha is like theta times x. So but x was del u by del x. Okay, and so theta is the same here he's taking. So I can just write like this: del u by del y and del u by del z. So del u by del y is the capital Y. So this is the beta minus theta of del u by del y, and then minus theta of del u by del z was gamma. Okay. So this is nothing but the gradient descent method that he proposed, right? So I can call this whole thing as a vector x, and then minus the step length theta, and then this is nothing but the gradient of f, or in this case you can say u. So in this case we can say u, gradient of u at x bar. Okay, so this is the origin of the gradient descent method. And then he goes ahead and gives some proof that if you indeed update your x like this, if you indeed update your x like this, then the function is going to decrease in value, because this is a positive quantity and this is your original output u. So you are certain to decrease by subtracting. So by subtracting some certain positive quantity, you're definitely going to decrease the value of u. And that's why he's saying that this algorithm will decrease the value. And this is happening because because gradient points in the direction of the increase, and he took the negative of the gradient. So in some sense, you can say that there is an implicit proof of that argument that going in the direction of the negative gradient will decrease the function value. Okay, and it will decrease by like this much, theta times x square plus y square plus z square. Okay, so this was the like historical context of how the gradient descent method came in picture. And yeah, and then like, and this is what he is like trying to now explicitly like say. Okay, so and he is also saying like where where it will arrive when it is minima. So it's saying it's written in French, right? So I can read French, but yeah. So but this is the translation here that you can see. Okay, so he's saying that like at the minimum value, we will have this where the gradient will vanish. Okay. So now your question is for which functions gradient descent is guaranteed to find extrema. Okay, so remember a function can be very general or like oscillatory or something like this, right? And the problem in this type of function is that there are multiple local minima and maxima. So this is like local minima, this is like local maxima, but sometimes you may be interested in like finding the global maxima, let us say, or let us say if this is the global minima, then you may be interested in this. So gradient descent, as I said before, since it follows the gradient, it will not be able to find the global maxima. It may, let us say this was the local maxima. So if you started from somewhere, it will push you in this direction and then you get stuck here. Okay. But you know that the global maxima, the maximum possible value over all domain was actually here, but the gradient will get stuck here. Okay. So how do we characterize those functions where that has only one maxima, one global maxima, or there are no local minima or maxima, right? So this is one question. These are set of functions for which global maxima or minima is guaranteed by gradient descent method, because there is only one let us say minima. Okay, global minima is there. There are no local minima, so there is no point that you are going to get stuck. Okay, so we are trying to formalize things here. Like we would like to systematically study these optimization methods. So first we will say, okay, what is the simplest case where I am guaranteed to have local minima? Okay, so let us fix only minima problem. As I said, maxima is just the equivalent form, right? So let us focus on, let us say, only minima. So what are the set of functions for which I will only have a global minima? And then in that case, from the gradient descent method, actually we know that we will arrive at that local minima because that is guaranteed. Okay. Only problem with gradient descent is like when there are multiple local minima. So in that case, I may get stuck. So we can start with the basic case where we will say which are the class of functions. Okay. So we are looking for a class of functions for which gradient descent will find the global minima. Okay, so that is where we will be led into class of functions, so-called convex functions. Okay, so we would like to introduce convex functions, but even before defining convex function, we would like to understand what are convex sets. Okay, so that will be our next step. So let us look into convex sets. Okay, so convex set, a set is convex if every line between 2 points stay in the set. Okay, so literally intuitively it's very clear to you by now. A set is convex if every line between 2 points stays in the set. Okay, so for instance, I take 2 points like this, and then I join like this by a line. Then the whole line is inside this shaded region. Okay, similarly, I take any 2 points, you give me any 2 points, and then I join the line. Then all the points joining the line is still within the set, then it is a convex. Okay, so you can think about any 2 points. Okay, so any 2 points within the set, if I join it by line, so everything is inside the set only. Okay, it's not going outside. Okay, straight line. Okay, it cannot be curved, right? If you ask for a curve, then it will not work, right? So it is a curve joining two points. So definitely many parts of the curve are outside. Okay, so we are talking about line only. Okay, so for instance, for instance, sets like this are not convex, because if I take a point here and if I give you a point here, now you have to join it by a line, right? So if you join it by a line, then it will be this, but some part of the line is now outside the set. Okay, so hence it's not a convex set. So mathematically we can write it like this. Okay, so x1 and x2 are 2 points. X1 and x2 are 2 points. Then what is the equation of a line that starts from x1 and ends at x2? Okay, so we can write this in parametric form like this. So you can check this that this is actually the line joining x1 and x2. So if I have x1 here, if I have x2 here, then at theta equals to 0, actually I'm here. So the line is like this. Okay, so at theta equals to 0, you will see that you are at point x2, and then at theta equals to 1, you are at point x1, and for any intermediate value, let us say theta equals to half, then you are at the midpoint. Okay, midpoint of so this is the midpoint x1 plus x2 by 2. So by doing a continuous variation of theta between 0 and 1, I can get all the points between x1 and x2, which means that I get the whole line joining x1 and x2. Okay, so this is what this definition is trying to say here, that a set is convex if every line joining 2 points stay in the set. So this is what concretely I can say, that if x1 and x2 is in the set, then theta x1 plus 1 minus theta x2 is also in the set. And if this happens for all x1, x2 in S, then that is called a convex set. Okay, so that's the definition of a convex set. There is another general definition of a convex set is, and both are equivalent. So it says that you take, rather than saying only 2 points, you take any set of points and you take all convex combinations. Okay, so there is a difference between linear combination and convex combinations. Okay, in a linear combination, if you recall, we write the vector u as alpha 1 plus alpha n vn. Okay, so this is called linear combination because there are no restrictions on alpha, no restriction on alpha I. But in convex combination, the sum of these scalars, okay, must add up to 1, and that is called convex combinations. Okay, given a set of points, convex combination is summation of theta I xi plus summation of theta I must be equal to 1, and also additionally theta I must be greater than or equal to 0 also. Okay, so this is the definition of convex combinations. So the basic definition is this. Usually you will use this, but one can also use this as a definition for convexity. So what this is trying to say is, like, I pick, let us say, any number of points. So let us say I pick this point, this point, this point, and this point. Okay, then it is saying that any convex combination. So if you do a convex combination of this, you will see that actually it will fill everything inside. Okay, so you will see that it will fill everything in the inside. Okay, so if it fills everything, so what this second definition is trying to say is, like, you take any number of points in the set, and if you take a convex combination, then in that case this will fill. Then all the points that you had generated after doing convex combination, that should also lie in the set, which in this case is true. Okay, so you can take any number of points. Okay, like this, like this, like this. Okay, like this. If you take a convex combination of these boundary points, then again you will end up with filling the whole of this. And if it so happens that all the points still lie in the set, then it's a convex set. Okay, this is an equivalent definition. You can say that it looks more general, but it doesn't matter. Okay, actually one can prove both ways. So So convex sets are defined like this. So one can prove that both the definitions are the same. Okay, actually proving from here to here is a straightforward thing, because you are already given that all convex combinations lie in the set. So definitely for x1 and x2 also this thing holds, and sum of theta 1 theta 2 theta 1 plus theta 2 is 1. But this is exactly happening here also, because I can choose this as theta 1 and theta 2 is as 1 minus theta 1. In that case, theta 1 plus theta 2 will sum to 1. Okay, so that will satisfy this. So going from here to here is trivial, but you can also actually prove this way. Okay, you can try to prove how actually the first definition actually implies the second definition also. Okay, you can try to prove that. Okay. So this was convexity in a finite dimensional vector space. Okay, so what for our case we will be always be dealing with Rn. So this is our vector space we saw in the previous classes. So these are the vector spaces that you will be working with. It is very rare that we will choose any other vector space. Okay, so in reality we always work with Rn. Okay, so so this is the vector space, and we know that and we can also define inner product and so on, norms and so on. So this is really also a inner product space. So I can define inner products to be like this. Let us say y transpose x. Okay, so this is the inner product, and then I can also define a norm in this vector space. Okay, so norm is x comma x, and then square root of that. Okay, so so in a vector space I can define an inner product. So this is the standard inner product in Rn, and I can also define a norm now using the inner product. Okay, so inner product does give you a norm, but not all norm come from inner product. Okay, so this inner product does give me a norm. And why do we need norm? Norm gives the concept of a length. Okay, so norm plays a very important role. We will see this in the upcoming classes. But for the moment, what we know is like we have a vector space. We can define some inner product space. And then once we have inner product space, we have a geometrical meaning of, we have some geometrical concepts here of perpendicularity, parallel, and so on. So if this inner product, let us say, is 0, then we say that they are the vectors are like orthogonal and so on. Okay, so it gives us some geometry, geometrical structure and so on. Convexity can be defined also in a very general spaces. Okay, so but we can skip those things. This is not very important in our case. So by general spaces I mean like metric spaces and so on. Okay, so metric spaces are quite general, but we can skip that. That's not very important in our course. So I may have to stop here for today. So I will continue with convex sets. Then we have to go to convex functions. Remember, convex function is gives you the guarantee that you have a global minima, and for that the convergence is guaranteed. Okay, and after that we will look into variety of optimization. We will actually go to steepest descent, and we will say what role the norm has to play. Okay, so we have seen the basic gradient descent method, but there are a variety of that. Okay, so we will see a wide variety of these and how to derive those different type of solvers. And then we will get into variety of optimization model itself, constrained, unconstrained. So how will you apply these solvers, the so-called iterative solvers, to solve variety of models that you encounter? So this is the thing we will do next. So with this I will stop here. So it's like 2:30 now, so I can stop here and we will continue in the next class. If you have doubt, then obviously you can also now ask in the tutorial. I asked them to review the linear algebra thing. Okay, so linear algebra will be reviewed in the tutorial.